Hi everyone, this is Chen. I am a system architect from 4Paradigm. This is a joint work between 4Paradigm, National University of Singapore, and Intel. Over the past decades, AI has increasingly attracted a significant amount of the attention from both academic and industry. Online decision augmentation has been widely used in many applications, such as real-time fraud detection, personalized recommendation, production forecasting, and so on. 4Paradigm is an emerging pioneer who provides enterprise-granted OLDA solutions to more than 8,000 customers during the past 5 years. In this study, we first use a real-time fraud detection system as an example. It has been already deployed in the top bank in China. We developed and analyzed the entire workflow to summarize the characteristics of the OLDA applications. As shown in the figure, when a user swaps the credit card through a POS machine, it will generate a new original recall. After receiving the recall, the OLDA system first inserts the new transaction into an in-memory database, then immediately extract the feature based on the user's historical behavior. Those features are fed into a pre-trained machine learning model and score and predict the probability of the fraud. Both the user's behavior as well as the fraud result will be used as a feedback for offline training system. The entire OLDA cycle, the online fraud inference process is executed under a strict time constraint, which is also the main focus of this paper. After profiling, we have identified that the real-time feature extraction is a performance bottleneck. As shown in the figure, feature extraction can be recognized as obtaining the hidden information in the raw data, and it has the following characteristics. Firstly, most of the real-time features cannot be pre-extracted until the new record is received. Secondly, most of the real-time features are time-related and require top-end to be computed over multiple time windows. Based on our experience, the more time windows are involved, the more accurate the predict will be. Lastly, in practice, OLDA system extracts thousands of the real-time features for each prediction, which dominate overall response time. The feature extraction workflow is quite different from the traditional database workflow. We have evaluated such workflow over a series in-memory database. Here, we list the two state-of-the-art commercial in-memory databases that we will not name publicly. The latency of both DBX and DBY are more than 100 milliseconds, while the number of the time window larger than 3. In practice, our fraud detection system requires finish such operations over more than 10 time windows within 100 milliseconds. It is obviously that both of them cannot meet our requirement. Motivated by above observations, we propose feature engineering database. FEDB is an in-memory database engine specifically designed to support online feature extraction. It consists of two parts, FEQL and storage engines. FEQL is a circle-like language which not only supports most of the standard SQL, but also introduces some new syntax. For instance, FEQL can define multiple time windows in a single query so that the execution of those top-end queries can be optimized. In the storage layer, we adapt a DRAM-based double-layer Skiplist as an index. The time window query can be performed by search the first layer Skiplist for the specific key, followed by a scan the second layer Skiplist for the given time window. We compare our FEDB with previous commercial database. In FEDB, consistently outperform the both database. More importantly, the results show that the more time window are involved, the bigger the performance advantage FEDB gains. After deploying the fraud detection system to the bank, we find the DRAM-based FEDB has the following limitations. First, the fraud detection system occupies around 10 terabytes to store data in memory. Both the huge memory consumption and the limited size of the DRAM capacity per server significantly raise the total cost. Second, The traditional in-memory database have to sync data from volatile DRAM to slow HDD or SSD. The tail latency can be too high to meet the strict time constraint, while workload is heavy. Lastly, the traditional in-memory database take a few hours to load data from the backup storage to the DRAM after failure. Such long recovery time affects the system availability. Compared with DRAM, Intel Optane persistent memory, which is also called PMEM, has much larger capacity. It is also bioaddressable and non-volatile. PMEM gave us a good opportunity to address above limitation, and it can work in two modes, memory mode and DRAM mode. In memory mode, PMEM is working as a system memory, while FDRAM mode provides a way to direct access PMEM as a bioaddressable persistent device. In this work, we choose FDRAM mode and we remove the traditional log and the snapshot flash process. We propose a PMEM-based persistent skiplist. Most of the PMEM data structure apply logging or copy and write to guarantee the consistency. Those approaches are not efficient. Here, we introduce persistent compare and swap mechanism. As we know, CAS is an atomic instruction used in multi-threading to achieve synchronization. However, the traditional CAS may cause an inconsistent issue while applying on PMEM, since CAS and the CPU flash command are totally independent. We first solve the CAS correctness issue by using a flash on read strategy, which means we flash the data before read to guarantee the correctness. Meanwhile, to avoid unnecessary flash on clean data, we leverage a smart pointer whose lower 4 bits are used to identify whether the data is clean or dirty. We redesign the process of the insert, delay, and search in the persistent skiplist using PCAS. To further reduce the amount of the PMEM write, we only store the last layer of the skiplist and the data on PMEM. Thus, we develop a recovery process to rebuild the whole skiplist when system failure. In the experiment part, we use our real-time fraud detection workflow to evaluate both DRAM-based, PMEM-based FEDB, as well as two state-of-the-art commercial in-memory database. The data size of the workload is shown in the upper table. We deployed 3 replicas, so the total size of the memory is around 10 terabytes. We first compare the TP15 latency among all databases. The result shows that FEDB can achieve up to 37 times to 610 times faster than the state-of-the-art database. Then we use DRAM-based FEDB as a baseline to compare the performance of different PMEM-based FEDB. The result shows that the PMEM-based FEDB can shorten the tail latency, reduce the recovery time, and save the total cost of the ownership significantly. We conclude the paper. In summary, in this paper, we first characterize the real-world OLDA. We propose FEDB and then use Intel PMEM to solve the limitation. We evaluate the real-world workload on database to show the promising result. Now, we already open source both the PMEM data structure as well as our FEDB, now renamed as OpenMLDB on Git. For Paradigm and Intel, also build a technical community called Memory Arc, focusing on modern memory and storage architecture. We're also listing a PMEM version Kafka here. You are welcome to download and try. Thank you.